correct?
Yeah, yep.
Okay. And how long you've been working on it?
Like 6 months, I guess. Yeah,
All
I
right.
started last semester. Yeah.
All right. Just a couple more minutes.
Okay. Shall I start now, I guess?
Yep, the floor is all yours.
Okay, thanks. Hello everyone, and thanks for tuning in. I'm Supun Abesinga. I'm a second year PhD student, and I'm working with TIA. And today I'm going to be talking about an ongoing work where we try to leverage generative programming for building efficient end-to-end data science pipelines. So here's an outline. I'll be introducing what is generative programming, and we'll look at two systems that are built using these techniques. And then we'll be looking at a specific use case and try to see what we can do to optimize things in a stepwise manner. So, what do we mean by specialization is, let's take this power function as an example. So here it's basically computes x to the power n. And when we say we specialize this program to n equal 3, and let's assume that we know the value of n at the current stage, and we do not know the value of x, right? So if we know the value of at current stage, for example, n equal 3, we can specialize this program to that value. So when we specialize this program, we get this program. So we no longer need to have the recursion, because the recursion depth we can we know, because we know the value of n, right? So there's a technique called lightweight modular staging to do these kind of programmatic specialization with the help of the programmer. So lightweight modular staging, or LMS, is a type-driven approach, and the most important part is these rep types. So basically, these rep types represents variables evaluated at the next stage. So simply something we do not know at the current stage, right? And these rep types, so for example, rep string, rep int, or whatever, operations on these rep types would generate code, which will be executed later when we have the exact value of those variables. And anything other than rep types, these rep types will be evaluated at the staging time. So string or int now, int would be executed. It simply as a um, so normal variables. So this is pretty much the same example we had in the earlier slide. So here, let's assume arg is something that the user imports. And simply here, we know the value of n here, and we can specialize this program to the value 5. So it gets simply replaced by this. So here x is a rep type because we do not know the value of x, and n is simply an int. So yeah, so what happens underneath is so these rep types or rep objects basically sort of behaves as a wrapper, and whatever the operations we do on these rep types will be recorded and then gets mapped into an intermediate representation, and then this intermediate representation will be used to generate this code. And this intermediate representation will go through multiple optimization passes and transformations, right? So in this example, we have seen going from a Scala source to another Scala source. So the target here is also Scala, but we can go a step further and we can generate something like this, like C, native C code. So the benefit of doing that is now we can write these programs in higher level abstractions, like using the Scala type system and using Scala objects, traits, and whatnot, and still generate this kind of low level code that would be highly performant, right? So yeah, so this can be executed independent of this. So we use this program and then use LMS to generate this program, and then this will be compiled using GCC and can be executed. So we no longer have the overhead of like the JVM overhead and stuff like that. So this notion of runtime native code generation is really powerful and is in fact used in multiple systems. One of the example is Flare. So Flare is an accelerator for Apache Spark. And so Flare basically uses this technique LMS to generate runtime native code from optimized query plans from Spark. So if you're familiar with Spark, Spark has multiple front ends, and Spark has this API called data frames. So you can think of this as a normal query execution plan. And then this optimizer called Catalyst is, it'll take this query plan and do certain optimizations and then output an optimized query plan. So if we use Spark, then it'll do code generation into this native Spark native RDDs. But when we use Flare, what we do is we export this query plan, optimized query plan, and then perform code generation using LMS. So we are exporting this query plan, and then we would generate native code, which is in C, and we can compile that code and run that code independently of Spark. So whenever we are running this code, we can simply run it without the Spark runtime. And this is in fact has shown great success, and it has shown order of magnitude speedups over Spark for scale up workloads. And it is competitive with like highly engineered state of the art in-memory databases like Hyper from the database community. And another similar system is Lantern. So Lantern also uses LMS and performs runtime native code generation. And yeah, it is a deep learning framework. And so it expresses backpropagation or reverse mode AD using delimited continuations. But I'm not gonna be going into details. Yeah, so it is so backpropagation can be expressed using delimited continuations. And so one special thing about Lantern is it has the expressiveness of defined by run frameworks. So frameworks like PyTorch, and it has a performance of defined then run frameworks like TensorFlow, where we explicitly create a computation graph and then do optimizations and then schedule it to run. So and also Lantern is expressive in the sense that it can support machine learning models with control flow like if statements or while statements and etc. So that is about Lantern, and Lantern, the performance of Lantern is on par with other machine learning models when it comes to state-of-the-art models like transformers or deep speech, SqueezeNet, etc. So then let's look at how we can build end-to-end data science pipelines. So typically when we build these kind of data science pipelines, we use different frameworks or systems. So for instance, we use something like Pandas or Spark to do the data manipulation. And then we use a downstream machine learning framework like TensorFlow or PyTorch to handle the machine learning. So let's look at a specific use case. And so in this use case, we'll be looking at a sales forecasting dataset from Kaggle, and it consists of 6 tables and has more than 125 million records. And yeah, so these kind of data sets are pretty common in Kaggle. In fact, from a Kaggle survey, it has been yeah, it has shown that these kind of relational data sets with multiple tables are one of the most common data sets. So we can start with a simple approach. So as I said earlier, this pandas and PyTorch approach is one of the most commonly used approaches. This is because it's an intuitive Python API, and yeah, it's easy for even for someone new. And so this is the performance for that case. As you can see, it takes a lot of time to do the data processing. So specifically joining these 6 tables into a single relation, it takes a huge time. And also data loading, even data loading has a significant overhead. So what could be the reasons for this overhead is, so one of the biggest reasons is Pandas only supports single threaded execution. So it cannot leverage multiple cores or multiple threads in the machine. And then the general inefficiency of Python, like the interpretive nature and um, the overhead of the Python runtime. So we can accelerate this by using something like Dask. So Dask actually parallelizes pandas by operating on chunks of pandas data frames. So basically, a single large data frame would be split into multiple chunks, and then these operations on so data processing queries will be operated on these chunks and independently, and then the final result will be created by merging these partial results. So as you can see, we see a good speed up compared to Panda's data processing, like around 1.6x speed up uh, for data processing. But yeah, one question one might ask is, okay, can we do better? So the natural next choice is to use something like Spark. So Spark is the de facto standard for big data processing, and it has shown, yeah, it is one of the most widely used approaches to do this kind of big data processing. And as you can see, when we use Spark, we can see a significant improvement in performance. And if you consider the data processing time, it shows like almost 3x speed up over this Dask and PyTorch approach. But now we have a different problem because Spark is running in Scala, and Python, PyTorch is in Python, and there's no like efficient way of communicating or transferring data from one framework to the other, right? So we see a significant overhead in terms of data conversion cost here. And yeah, so as I introduced earlier, we can replace Spark by Flare. And so Flare, as I said earlier, Flare accelerates Spark by runtime native code generation. And once we replace Spark with Flare, we see a significant improvement of performance over Spark. And yeah, you can see it's running the data manipulation query pretty fast compared to Spark. And now even in this case, the overhead exists because Flare generates native C code and executes the binary. And there's no efficient way of directly transferring the output of Flare into PyTorch because PyTorch runs in Python. And yeah, now the bottleneck is basically at the system boundaries, and it significantly has an effect on the end-to-end performance. And we can try to, yeah, so we can try to eliminate this overhead as system boundary. So this is caused by inefficient IO and inefficient CSV passing overhead. So instead of using PyTorch here, we can replace it with Lantern. So we have seen that Lantern uses LMS to do runtime native code generation. And we can add an efficient CSV loader to Lantern and then do this CSV parsing more efficiently compared to PyTorch. So yeah, so we can replace PyTorch with Lantern, and now we have a more efficient CSV parsing approach. And yeah, so you can see that the data conversion overhead is significantly lower than passing the CSV from PyTorch. So yeah, we have improved the performance, yes, but still this is still the performance bottleneck. And are there any efficient ways of eliminating or reducing this performance overhead? So whenever we are using CSVs, we need to incur the overhead of parsing. But if you use something like a binary format, we can directly get the results or get access to data without without any passing overhead. So we can plug in a binary store, and basically a mechanism to save or dump the final output into a binary format. And from the machine learning side, we can add loader to load this binary files. And so here we need to agree upon a common binary format. And then, yeah, so basically these would be really efficient because even these binary stores and binary loaders could generate low-level C code. And yeah, it significantly reduces the overhead of parsing CSVs, and we can see good performance improvement over our previous approach. And yeah, so then can we even further, optimize this performance even further? And yes, there is another way to do it. And a way to optimize this is using this command IR. So basically, we write Spark programs and exports the query plan into Flare. And then Flare uses LMS to generate a single piece of low-level code. And Lantern, we write the machine learning model in Scala, and then we use LMS to generate low-level code for that particular model. So then we would compile this code and compile this code separately, and then there would be some indirect way of communicating between the two systems. And that is what we did earlier, right? So rather than doing that, we can, since both of these systems use the same generative programming approach, we can actually combine these two systems at the same IR level and bring these two systems into a common intermediate representation, right? So yeah, from Flare and Lantern, we would build a single intermediate representation. And then since we have a single intermediate representation, we can generate a single piece of low-level code, and it'll be for the end-to-end task, right? And so again, since we have a single intermediate representation, we can do certain optimizations that weren't possible before at a global scope rather than at independent system levels. So when we combine these two systems at the IR level, we can see that this overhead of data conversion or data transfer is eliminated, and we get a significant performance gain by combining, building a single end-to-end pipeline. And can we do more optimizations? So this is particularly for the case where we execute things in the GPU. So specifically, whenever we are copying data from the host, the CPU, to the GPU, uh, there is this notion of pinned memory and pageable memory. So whenever we are copying data from the CPU to GPU, what happens is the CUDA engine would temporarily allocate a region called pinned memory, and then copy that data into pinned memory, and then that memory from the pinned memory will be copied to the DRAM. So rather than doing that, since we have access to a sorry, access to a end-to-end pipeline or end-to-end single source file, we can actually allocate this pin memory directly for the output of the data processing engine. So the data processing engine would directly write to this pin memory, and we can eliminate this copying from pageable to pin memory when we do the data copying from the CPU to GPU. So we can do this, and it has shown that this can improve the performance around 10% in terms of the end-to-end performance of the whole system. And so one other thing we can do here is we can pipeline computations to the GPU. So generally what would happen is we would complete the data processing, and then we would copy the data and then run the machine learning kernels. But yeah, so we do this because there's no way of communicating while the data is processing, because if the two systems are independent, right? But now, since we have a single source and everything is in the single address space, we can pretty much interleave these operations, right? So as we produce records from the data processing engine, we can asynchronously copy data from the GPU to the CPU, sorry, CPU to the GPU. So we can basically get a performance benefit out of it. And we can go a step further, and this is particularly for inference workloads. We can do the copying asynchronously, and we can even do the inference, launching the kernels asynchronously as well. So this would also improve the performance of the end-to-end performance of the system significantly. So, so where are we now? We started with this pandas and PyTorch approach, and we said it is the most common approach because, for good reasons, right? Because it's Python API and it's widely used. But the problem is it's really slow, right? So it takes more than 300 seconds to do the computation. And then there is this approach, the approach we presented, and it is pretty fast. It runs significantly faster than the pandas and PyTorch approach, but the API is in Scala, so you have to write things in Scala, and it's not Python. And people, the community would not take it if it's not Python. So is there any way to bridge this gap, having user-friendly APIs and having good performance? Actually, we can do it in our system. So as we discussed earlier, Flare operates on optimized query plans from Spark, and Spark has this front end called Koalas, which is exactly like Pandas like API, a Python API to do data frame and data manipulations. And then for the machine learning side, there is a framework called Snake, which basically can convert PyTorch code with minimal annotations into Lantern. So we can have something like a PyTorch syntax in the front end as well. So that means we can support this Pandas and PyTorch API from the front end, and we can still gain the benefits that these kind of speed ups over the initial approaches. So that is what we did. And in terms of conclusions, we can see there's a big performance gap between widely used approaches to build these kind of end-to-end pipelines and implementing them in native code. And generative programming helps bridging this gap between these approaches. And so these kind of approaches have the ability to keep user-friendly APIs in the front end, and also have the ability to perform or have best of the breed performance in individual workloads. So as we seen earlier, our system performs or is competitive with state-of-the-art DBMS systems for full relational benchmarks like TPC Edge, and is competitive with existing approaches to build state-of-the-art machine learning models like transformers. And also this enables cross optimizations at the IR level compared to having independent systems. Once we have a single, once we can build a single pipeline, we can do cost optimizations, which results in state-of-the-art performance at the end-to-end level as well. And yeah, in terms of the engineering effort, it is minimal compared to engineering something like this from scratch. And with that, I'm concluding my talk, and I'm happy to take any questions. And thank you.
Hey, this is Tiak. Nice talk. Question. So let me play the devil's advocate a little bit. So it seemed like a lot of the improvements you showed actually came from, you know, things that one could say are low-hanging fruit, right? So switching from a CSV to a binary file format or something like that. So conceivably, you could get those benefits by, you know, just, you know, deciding on a binary format and then implementing like a parser for that format as part of PyTorch. Wouldn't that give you like, you know, 90% of the performance improvements that you showed?
Yeah, so if you compare the performance from the initial version to this, yes, most of the performance is gained by simply replacing the data processing and machine learning, and having, I mean, this overhead is not that significant in terms of this what we had initially. But when we go into like this level, we can see that I mean, if we write a custom binary loader in PyTorch, we would still have some overhead like this. And
right, but this is actually something I don't understand. So this is data conversion, right? You're saying that's data conversion?
Yeah.
So what is being converted there?
Yeah, so basically it'll write it into a disk. So it can be data copying as well. I mean, it's not exactly conversion, it's copying.
So, but assume, so let's say I'm willing to modify PyTorch just a little bit, right? And, you know, implement like some, you know, low-level interface for either like reading from a file or, and I mean, reading to a file, you know, writing and reading a file is still slow, right? So let's say I'm actually building like an in-memory interface, right? Or I'm not writing to a file, I'm just using a pipe or something, right? So wouldn't that get me much closer than what you're showing?
Yeah, so I think it would come close. I mean, it would come in between this, and yeah, so most of the performance gains are caused by, as you indicated, by replacing frameworks and relying on a fast query engine. But if we use something like that, we won't be able to do these kind of optimizations.
Right. So I think this is important to stress, right? And sort of, I think these are questions sort of, I think, next time you give this kind of talk, right? I think it would be good to anticipate those, right? And sort of, preemptively say, hey, there's certain things we could think about, right? So I mean, clearly we can say, okay, let's just, I mean, we don't have to write to a file, right? I mean, in some sense, that's like, tying our hands behind our backs, right? So, it's a good first step, right? But sort of if we're willing to spend a little bit of engineering effort, right, then we don't have to do that, right? So there are faster ways of doing that, right? Sort of you can just like modify, take whatever like high performance in memory query engine you have, right? Take whatever the fastest machine learning framework is you have, and sort of do the minimum necessary modifications to make them communicate, right? Standardize on a binary format, make one write into a buffer and the other one reads from the buffer, right? So then the question is, okay, why is that not enough, right? So what do you do that actually improves things further, right? And why is that interesting, right? And I think sort of that's my other point, right? So I mean, speedups are good, right? So but in the end, we're not at the Olympics, right? So it's not just about, okay, yes, I eked out some 20% performance gain, right? But there's intellectual stuff, right? So there's an intellectual story here, right? And I think that's another thing that's sort of key to highlight, right? So and the other question is, of course, sort of when you talk about, okay, yeah, generative programming allows these kind of things, right? And sort of a common IR is kind of critical. Then sort of the devil's advocate question for that is, okay, why don't you just use LLVM and be done, right? So I mean, can we get the same benefits of just using LLVM IR, and then maybe there's a low-level transformer implemented on LLVM or MLIR or something like that, right? And yeah, so is there anything beyond, right? I think this is these are questions reviewers might have, right? Or if you give the talk at the conference, then these might be questions people might be having.
Right.
Okay, and just general feedback in terms of the structure. I think I think in the beginning, sort of you had the background was very extensive, right? So you kind of ticked all the boxes in terms of background, right? You talked about Flare, you talked about Lantern, you talked about Spark, and so on and so on and so on, right? So it was very comprehensive, right? In some sense, that's useful. But especially if you're giving a shorter talk at some point, right? Then I think you just don't have the time, and you will just lose the audience because they are waiting for you to get to the core contributions, right? And sort of while you're going through the background, everybody's like, okay, yeah, I heard about that, or maybe I'm not so familiar with that, but why does this matter, right? So tell me what this is about, right? So I think sort of changing the order might be beneficial, right? Sort of talk about, and this is again something what I mean when I talk about telling a story in a problem-oriented way, right? So you want to start with the problem, right? And that can be relatively short, and you've got to be concise, right? You got to say, okay, people are, for contemporary, data analytics, right? You want to have like SQL kind of things and ML kind of things, right? And you got to put them together, but the systems aren't designed for that, really, right? So and then you can sort of show your like initial performance and say, okay, this is we can. So here's the starting point. Here's where we get, right? And in the rest of the talk, I'm going to show you how we got there. Right? So I think this is one thing where you can on slide 1 and 2, you can make it clear to everybody. This is what this is about, and this is where it's going. All right. And if you can show people on slide 2, okay, we're getting 100x speed up, then people are hooked, right? And then you can sort of introduce background, only as much as necessary while you're talking about how you're achieving certain steps.
Right.
Good. Anyways,
Yeah.
I don't want to
Thanks.
monopolize the Q&As. Anybody else has free to go ahead.
Yeah.
So I do think anybody else from my group, Wanan, Yuya, and you should add some pro.
Yeah, I think it's a very interesting chart, but I was wondering, like the IR design part, it seems, because it seems just highlighted there, but some of the detail is not really fleshed out. I would like to know more a little bit how those IR is get fused or get designed.
Right. You mean like, okay, to be more detailed about, for example, how we combine these things?
Yeah. For someone like me, if I already know something about RMS, I can imagine something, but for readers who don't know RMS or don't know IR in general, it's maybe curious about how does those two different IR domains combine together and how they can work together and have this performance output.
I see. Yeah, that's a good point. Thanks. Yeah. Yeah, I mean, if no one else has questions, thanks everyone for your attention, and thanks Pedro for giving me the opportunity to speak. Yeah.
Thank you so much for presenting, man. It was great.
Thanks.
See everyone next week then.
Thanks, and see you.
Double check.
Yeah.
Okay, we have a viewer go out. So yes, we have external speaker. Exciting. All right, see everyone next week.